Have you ever wondered why some electronic components are considered ideal in theory, even if they do not quite exist in the real world? It is often to simplify complex analyses and highlight core principles. An ideal operational amplifier, or op-amp, must have an infinite slew rate because this characteristic dictates that its output voltage can change instantaneously in response to any change at its input. Slew rate refers to the maximum rate of change of the output voltage of an op-amp over time, typically measured in volts per microsecond. For an op-amp to be truly ideal, it cannot introduce any delay or distortion when its input signal changes, no matter how quickly. If an op-amp had a finite slew rate, its output would lag behind rapid changes in the input, especially with high frequency or large amplitude signals. This limitation would cause signal distortion and prevent the op-amp from accurately reproducing the input. The ideal state assumes perfect fidelity and speed, meaning the output adjusts without any temporal constraint, perfectly tracking even the fastest transitions, thus maintaining the virtual short between its input terminals at all frequencies. This infinite speed implies that the internal capacitors, which limit the speed of real op-amps, charge and discharge instantly. When we analyze circuits with ideal op-amps, assuming an infinite slew rate simplifies our calculations significantly. We can focus purely on the voltage and current relationships without worrying about dynamic response limitations. This lets us derive fundamental circuit behaviors like gain and filtering characteristics easily. In practical design, however, engineers must select real op-amps with a sufficiently high slew rate to avoid slew rate limiting, which causes a distorted, triangular-like output when a sine wave input is too fast or too large. This ideal characteristic underpins the concept of power bandwidth, which is the maximum frequency at which a large amplitude output signal can be produced without being limited by the op-amp slew rate. Without infinite slew rate, the virtual short condition between the inverting and non-inverting inputs would break down at higher frequencies, leading to non-ideal behavior. An ideal op-amp avoids this entirely, ensuring perfect operation across all frequencies. Understanding the theoretical necessity of an infinite slew rate for ideal op-amps helps us grasp the fundamental principles of their operation and the core assumptions behind circuit analysis. It allows us to build a robust conceptual model for predicting behavior, which then serves as a crucial reference point for understanding and mitigating the non-ideal characteristics of real-world operational amplifiers.